Let us next discuss the notion of a basis of a vector space. So, a basis of a vector space is a set which is linearly independent and which is also a spanning set at the same time. So, let me start with the definition here. Basis. So, a subset S contained in V is said to be a basis of V if S is linearly independent and a spanning set of V at the same time. So, notice immediately that a theorem from our previous video tells us that if you throw out even one vector from a basis, then the span will be a strictly smaller set, and therefore it cannot maintain the spanning property. So, basis in some sense captures the bare minimum or the minimum number of vectors which is needed to span our given vector space. So, let us look at a couple of examples. The first example is probably R2 or R3. R2 will have a similar set. In R3, consider, so let me not use the symbol S, let me use B, which is equal to 1 0 0, 0 1 0 and 0 0 1. So, it is quite straightforward to check that B is both linearly independent and that it is a spanning set. So, maybe I will just show that it is linearly independent. B is linearly independent. For if A times 1 0 0 plus B times 0 1 0 plus C times 0 0 1 is equal to the 0 vector. If there is a linear combination which is equal to 0, then the linear combination, the LHS will just turn out to be the vector ABC being equal to the 0 vector, and that means component wise coordinate wise it is equal to the coordinate vectors of the 0 vector, and therefore we are done. We are done with the linear independence. I will leave it as an exercise for you to check that B is a spanning set of R3. So, check that B spans R3 or beta spans R3. Hence, B or beta is a basis of R3. Okay, so we now have one example of a spanning set. Okay, so is 1 0 0, 0 1 0, 0 0 1 and say 1 2 3. Is this a basis? Let me call it S. Is S a basis of R3? The answer is that no, it cannot be, because it is not linearly independent. I will leave it as a small exercise for you to get hold of the linear dependence of the set S. The answer is no, not. So, it is linearly dependent. Similarly, if you consider is the set S, which is given by say 1 0 0. So, notice that in this case, when our S was 1 0 0 0 1 0 0 0 1 and 1 2 3, it is still a spanning set. It is, though S is a spanning set. Let me just throw it out. Though S is a spanning set, it's still a spanning set, right? So one property is not getting satisfied, of that of linear independence. It is a it's not a linearly independent set, it's a linearly dependent set. That's why it is not a basis. And let's now consider this vector collection of vectors, wherein we throw out 0, 0, 1 and 1, 2, 3 from the previous example. Then the question is S a basis of R3? And before you go ahead, I will request you to think about whether S is a basis of R3 or not on your own, and come to a conclusion that S is not a basis. No, S is not a basis. Observe that S is contained in a basis B, because it is after all the first two elements in this basis, and basis to begin with is linearly independent. Therefore, this set is also linearly independent. A subset of a linearly independent set will also be linearly independent, right? Therefore, S is certainly linearly independent. However, the previous week's theorem tells us that if you throw out an element from a linearly independent set, the span reduces. It will become a strict subspace of the span of S. And in this case, the span of S was the entire vector space. If you throw out one of them, then it has to be a strict subspace. In fact, we notice that 0, 0, 1 will not be in the span of S here. So this is not a spanning set, though S is linearly independent. So these two examples are to highlight that both the properties, being a spanning set and that of being a linearly independent set, both should be satisfied. Even if one of them fails, it will not be a basis. So it's a basis if both the properties are satisfied. So yes, so this is not a basis. In fact, there are examples where, say, if you take, say, 1, 0, 0 and say 2, 0, 0, this is neither linearly independent nor a spanning set. It's not a basis clearly of R3. Alright, so let's maybe look at a different vector space. Consider P3 of R, maybe PE3 of R, let's put 3, no problem. And I would like to claim that 1x, x square and x cube, the monomials 1x, x square, x cube, this is a basis of P3 of R. Let me not spend too much time to check that for you. It's quite straightforward, just like in the case of 1, 0, 0, 0, 1, 0 and 0, 0, 1 in R3, check for the linear independence and the spanning property of the set B here. I would also like to state that 1 plus x, x square plus x and x cube plus x square is also a basis of R, P3 of R. And if I consider our set S to be, say, 1 plus x, or maybe 1 x, x square plus x and x cube, this is not a basis, though it is a spanning set. It's not linearly independent. Similarly, if you look at 1 x plus x square and x cube, this is also not a basis, though it is linearly independent, because it is not a spanning set. Alright, so we have seen a couple of examples and a couple of vector spaces and many examples of subsets which were basis and which were not basis for various reasons. Let's slightly make our example a bit more complicated. Okay, before we look at more examples, let's prove a theorem which tells us why studying basis is worthwhile. It's actually quite special. So the theorem tells us that you take any vector in our vector space V, then the vector can be written as a unique linear combination of elements in the basis or vectors in the basis. So, every element can be uniquely written as a linear combination of vectors in a basis. So, let us state the theorem. So, let V be a vector space with a basis, a finite basis. Yes, let me impose the restriction of finite here, finite basis B, which is defined as the set V1 to Vn. So, what the statement says is that we have a finite set V1, V2 up to Vn, which is both linearly independent and which is a spanning set at the same time. Then, for every vector V in capital V, any vector in the vector space, there exist unique scalars A1 to An such that V is equal to A1 V1 plus A2 V2 plus dot 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 An Vn. So, every vector can be uniquely written as a linear combination of the vectors V1, V2 up to Vn. Let us give a quick proof of this theorem. So, as I was mentioning, this is quite remarkable. So, given any vector, we have A1, A2 up to An uniquely determined in terms of V1, V2 up to Vn, where A1, A2 up to An are elements in R, so they are scalars. Alright, so let V be in capital V, then since B is a basis, it is a spanning set, so there certainly exists one linear combination of V1, V2 up to Vn, which is equal to, since B is a spanning set, there exists A1 to An in R such that V is equal to A1 V1 plus up to An Vn. So, certainly the existence part has been ensured by the spanning property of P. The only question is uniqueness. So, we will show that if we have any other linear combination which of V1 V2 up to Vn which is equal to V, it should necessarily be the same as the linear combination in terms of A1 A2 up to An. So, to do that, let us start with another linear combination. Suppose V is equal to B1 V1 plus dot 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 plus Bn Vn be any linear combination of V1 to Vn equal to V. What does that mean? That means that we already have one linear combination here, right? V is already equal to A1 V1 plus A2 V2 up to An Vn, and therefore, then A1 V1 plus A2 V2 plus dot 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 An Vn, which is equal to V, is also equal to B1 V1 plus B2 V2 plus dot 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 plus Bn Vn. But we are in a vector space, and our vector addition and scalar multiplication satisfy all the properties 1 to 8 in the definition of our vector space. Using many of those properties, I will leave it as an exercise for you to check that this implies A1 minus B1 times V1 plus A2 minus B2 times V2 plus up to An minus Bn times Vn is equal to the 0 vector in V. So, this is a linear combination of V1 V2 up to Vn which is equal to the 0 vector. But B, recall, is linearly independent, and the linear independence Why is it linearly independent? Because by definition B is a basis, and basis is linearly independent, and linear independence forces each of the coefficients to be equal to 0, because if even one of them is not equal to 0, then that is a linear dependence of V1, V2 up to Vn, right. Therefore, hence A1 minus B1 is equal to 0, 0 scalar. A2 minus B2 is the number 0, and so on. An minus Bn is equal to 0. This implies Ai is equal to Bi for all I equal to 1 to n. Therefore, the expression therefore there is a unique linear combination of V in terms of V1, V2 up to Vn, because you take any other linear combination equal to V, we have forced it, or we have shown that it is forced to be the same as the above. So, hence every vector in capital V has a unique, that is what we have just shown, linear combination, or let me just write it as can be written as a unique linear combination, can be written as an unique linear combination in B, and therefore we have proved our result. Okay, so we have seen a couple of examples. Let's now look at more examples. Let's look at a more complicated example. So, consider the example of a subspace we were considering when we introduced vector subspaces, which was namely let W be the set of all x, y, z in R3 such that x plus y plus z is equal to 0. Okay, so let us try to get hold of a basis for this subspace W. So, let us try to obtain a basis for W. So, should start somewhere. Let us pick some vector in W. You notice what are some arbitrary vectors, 7, 6, minus 13 or 20, 30, minus 50. These are all vectors in R3 which are in W, right. The sum of the coordinates should be equal to 0. Let us not make it complicated. Let us start with V1 to be the set to the vector V1 minus 1 comma 0, right. 1 minus 1 is 0, and then add it to 0, it will give you back 0. Then V1 belongs to our W, it is an element in our subspace W of R3. Okay, so is it a basis? So, if you just consider B to be equal to just the set consisting of 1 minus 1 0, let me not call it B because we do not know what it is. Let us say let S be this particular vector. Question: is S a basis? Well, it is a set consisting of one non-zero vector. S is certainly linearly independent. S is linearly independent. Now, the question that comes up next is it a spanning set? So, claim S is not a spanning set. In fact, I will explicitly give you a vector in W which is not in the span of S. So, let me just leave it as an exercise for you to check that our element vector was 1 minus 1 0. So, check that 0, 0, minus 1. Oh, sorry, that's not even in W. 1, 0, minus 1 does not, is an element in capital W such that 1, 0, minus 1 does not belong to the span of S, and therefore S is not a spanning set. Okay, but let us not lose hope. We obtained one vector 1, 0, minus 1 which is not in the span of the previous set. So, let us now do one thing, let us append this vector and call our S to be, maybe S was already used, let me call it B. I am writing B, so you should get the clue here. Let us just put the two vectors and ask the same question. So, question, is B a basis of W? So, I will actually leave it as an exercise for you to check that if you have a linear combination equal to 0, then A plus B is 0. Okay, let me just show it. B claim, you make a claim and prove it. B is linearly independent. This is the easier claim actually to show that it is a basis. You have to check both. Let us first check that it is linearly independent. Suppose A times 1 minus 1 0 plus B times 1 0 minus 1, I guess these were the two vectors, yes, is equal to the 0 vector. This would immediately tell us that minus A is equal to 0, minus B is equal to 0 and A plus B is equal to 0. The first two already tells us that A is equal to B is equal to 0 and it is consistent with the third, and hence yes, this forces A and B to be 0, which gives that B is linearly independent. Okay, how about the spanning property? So, let us take some arbitrary vector, let x, y, z be in capital W. But then what does that mean? I.e., x plus y plus z is equal to 0, or let us write z to be equal to minus of x minus of y, right. So, suppose, so to check that B is a spanning set, we need to get hold of some A and B such that, so we want scalars A and B such that A times 1 minus 1 0 plus B times 1 0 minus 1 is equal to x y minus x minus y, just replacing the z by minus x minus y because we know that z is minus x minus y. But this is nothing but A plus B minus A minus B is equal to x, y and minus x minus y. Maybe I should have picked a bit more carefully. This implies A plus B is equal to x, minus A is equal to y, minus B is equal to minus x minus y. Therefore, A is equal to y and B is equal to x minus y. A is equal to minus y and therefore, B is equal to x plus y. And therefore, yes, we have a spanning property here. So, therefore, B is a spanning set, therefore, a basis and hence a basis. Okay, so let us carefully look at what we did. What we did here was to get hold of a basis in an algorithmic manner. We picked some vector at random, picked 1 minus 1 0 and checked whether it was a spanning set, saw that it was not a spanning set, picked an element which is not in the span, appended it, and therefore, after appending we obtained a new set which was both spanning as well as linearly independent. If you notice carefully, there was nothing unique about the choices we made. We could have started off with, instead of 1 minus 1 0, we could have just started off with 2 minus 2 0 or 2 3 minus 5, something like that, and done the same procedure, and maybe we would have ended up with a basis. So this tells us that this construction, of course, basis need not be unique at all, and this tells us that the algorithm also need not give you the basis. There could be many bases. Plural of basis is bases, BASES. You could get you could end up with many number of bases through this algorithm. This was, however, done in a very particular subspace of R3. Let's try to get clue from this example. Let's take motivation from this example and try to give a general theorem which works for an arbitrary vector space. So, theorem. So, let V be a vector space and S contained in V be a linearly independent set. Also, let us pick some vector V which is in the vector space capital V, which is not in S. So, let V not in capital S be a vector in capital V. Now, two cases can happen, either V is in the span of S or V is not in the span of S. Let us consider both these cases separately. So, if V is in the span of S, let us see what happens then. Then S union V is linearly dependent. The appending of V to S destroys the linear independence, and S union V is linearly dependent. Not just that, appending this vector is of no use in terms of considering the span. Also, the span of S union V is equal to the span of S. That is what happens when V is in the span of S. How about if V is not in the span of S? Then, as already noted in the example of the subspace that we were subspace of R3 that we were considering, if V was not in the span, if you append it, in that case the linear independence was maintained, right? That is going to happen in any abstract vector space. Then S union V is linearly independent. Not just linearly independent, also span is strictly a superspace, or the span of S is a strict subspace of span of S union V. Contains span of S. Okay, so let us spend a couple of minutes trying to see the few implications. The first one, we have already noted that if you remove one element from a basis, then the whatever remains, it loses the spanning property. So, in some sense the basis is the smallest set, smallest number of vectors which will be spanning our given vector space. Look at what is being said by 1. If you start with a basis, that is already a spanning set. So, if you take any vector V which is not in our basis, then it is obviously in the span of the basis, because the basis is a spanning set, the given basis is a spanning set. Now, if you append this vector to our given basis, then 1 tells us that linear independence is lost. So, appending a vector destroys the property of B being a basis. So, basis in some sense is that optimal set which is linearly independent at the same time a spanning set. You remove one of them, linear spanning property is lost. If you add one of them, the linear independence is lost. So 1 is quite deep in that aspect, the statement 1. And what about 2? 2 is telling us that if you don't have a basis already, let's not lose hope. Pick some element which is not in the, pick some vector which is not in the span, append it, we get a bigger set which has a bigger span and which is again linearly independent. We have used 2 already in the example prior to this, wherein we obtained a basis in an algorithmic manner. Alright, so let us prove both 1 and 2. So let us first prove 1. So if V belongs to span of S, what does that mean? That means that then there exists V1 to Vn and A1 to, so V1 to Vn in capital S and A1 to An in R such that V is equal to A1 V1 plus A2 V2 plus dot 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 An Vn. Okay, so then by adding the additive inverse of minus V, we can write minus 1 times V plus A1 V1 plus A2 V2 up to An Vn is the 0 vector. But that implies that S, you notice that V is not one of V1 V2 up to Vn because V is not an element of S, and therefore S union V is linearly dependent. That's what we had set out to prove. If you notice, we also have to show that S union V has the same span as S. So we have already done a similar argument. So let us take some arbitrary element in the span of S union V. So let A1 U1 plus An Un be an element in the span of S union V, and by a very similar argument as earlier, let me give it as an exercise for you to check that A1 U1 plus up to An Un is in the span of S. We have already done a very similar argument earlier, and therefore we get that span of S union V is contained in span of S, but S is contained in S union V, therefore span of S is always contained in the span of S union V, and therefore with both the implications, span of S is equal to span of S union V. And with that we have settled 1. Okay, we are now left with proving the second statement. If V is not in span of S, then S union V is linearly independent. Okay, so let me just write it down. If V is not in span of S, we want then S union V is linearly independent and span of S is a strict subspace of span of S union V. Okay, let us prove that. Let us prove the first statement first, that S union V is linearly independent if V is not in span of S. So, suppose it is not linearly independent, suppose S union V is not linearly independent. What does it mean to say that something is not linearly independent? Then A1 V1 plus A2 V2 plus An Vn plus A times V is equal to the 0 vector. right? That is what it means to say that where v1, v2 up to vn are not the vector v, they are different vectors. There is some linear combination which is equal to 0 with not all ai's or and a together equal to 0. So, suppose a is equal to 0, let us look at what happens. This would imply that a times v is 0 and therefore a1 v1 plus a2 v2 up to an vn is equal to 0. But then v1 v2 up to vn are vectors in capital S which is linearly independent. Linear independence of S implies that ai is equal to 0. But that is a contradiction to our assumption that S union V is not linearly independent. This actually implies that S union V is linearly independent, right? That is not the case. So, A cannot be 0, but this is let me just say that this is which is a contradiction. So, this contradiction has come up because we assumed A is equal to 0, hence A is not equal to 0. But if A is not equal to 0, then again what is our assumption? V is not in span of S, right? Then let us just rewrite this equation star. Then star can be written as V is equal to minus of A1 by A times V1 plus dot 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 minus of AN by A times Vn. But that implies that V is in the span of S because V1, V2 up to Vn is a set of elements vectors in capital S, which is again a contradiction. Because we had assumed to begin with contradiction. We had assumed to begin with that V does not belong to span of S. So, something has to be wrong. So, yeah, that means this assumption has to be false, right? Therefore, hence our assumption that S union V is linearly dependent or not linearly independent is false, because if we assume this, we are arriving at some contradiction, i.e. S union V is linearly independent. False. Okay, that is good, because what do we know about the subset of linearly independent sets? S is clearly a subset of a strict subset of S union V, right? Also, we know this. Why? Because we assume that V is not even in the span of S, not just S, it is not even in the span of S, and therefore, S union V is a strict superset of capital S, which is, and we just proved that S union V is linearly independent. So, if you knock off one element from a linearly independent set, we have shown that the span by the theorem from the previous session, span of S is a strict subset of span of S union V. And that completes our proof.